Hey guys, I'm Ray, or Mr. Ray, whatever you want to call me. Today we're going to be learning about amino acids, the special cases of amino acids, which basically means, amino acids that have special side chains. So histidine, proline, glycine, cysteine. And we all should already know that a side chain adds our chemical properties to amino acids. So to start off, to understand how exactly these amino acids get these special cases or these special side chains, we have to go over the amino acid structure. So we should all already know this because I talked about this in our last video. Our structure is going to be a mountaintop backbone with a line off to the side. We're going to have our OH here, our double-lined oxygen here. That's going to be our carboxylic acid. And right here, we're going to have our R group or our side chain. And we're going to have our H2N amino group. So this is our basic structure of our amino acid, and this is going to help us understand exactly where these special cases of amino acids come from and which ones have our special side chain. So remember, our side chain is just going to make our amino acids different. And there's going to be approximately 4 amino acids with special side chains. And we're going to go ahead and talk about which ones those are and why they have special side chains, what they look like, and just maybe talk about a couple facts about each one of them. So we're talking about amino acid special cases, and I told you there's going to be 4 amino acids that are going to have special side chains, and those are going to be the amino acid special cases that we're talking about. So let's discuss them. So amino acid 1 that we're going to have is going to be histidine. Then our second one is going to be proline. Third one is going to be glycine, and our fourth one is going to be cysteine. So let's talk about histidine first. So histidine, pretty simple. The first reason that makes it have a special side chain, so our special side chain, is it's going to have an imidazole ring. Let me draw a little line over here to separate it off. And its imidazole ring is going to be amphoteric, which is going to mean it can react as an acid or a base at physiological pH. And what physiological pH means is going to be the acidity or basicity within the body. So really, to understand what all this means with histidine, yeah, I kind of told you what it means, but to visualize all this, I'm going to have to draw it out, kind of give you the structure, and I'm going to have to explain a couple other things so you understand what all this pH means, and amphoteric and physiological pH. So let's go ahead and start this off right here. So to understand this, you're going to have to understand something called the Henderson Henderson-Hasselbach equation. Now, what the Henderson-Hasselbach equation basically says is that if you have a pH that is less than your pKa, so your pKa is going to be your acid strength, then we are going to be protonated. And protonated means positively charged. Okay, pretty basic. So now if our pH is greater than our pKa, then we're going to be deprotonated. Okay, yeah, still pretty basic. And now if our pH is roughly equal to our pKa, we're going to be 50% protonated and deprotonated, which is basically the same thing as amphoteric. So to understand how we use this Henderson-Hasselbach equation, I just basically gave you a bunch of lines and words that still really don't mean anything to you probably yet. So I'm going to have to draw you like the actual picture of our example and to understand how all this is applied. So our example is going to include histidine reacting within the body. And histidine reacts within the body, within the cells of the stomach and the cells in the brain. And so let me get this picture drawn for you and get the steps lined up for us so we can really understand what's happening here. All right, guys, so we're talking about our example of histidine. So within the body, and I'm going to draw out step by step an example of how this is going to occur. So step one, we're going to be at physiological pH, which is going to be at 7.4. So remember, I told you the physiological pH is your acidity or basicity within the body. So let's just, to visualize this, let's just draw, a little body. So a little head here. Oh man, there we go. There we go, now we have a body. So we have a pH of 7.4. And we're dealing with histidine inside the body because it occurs in the cells of the stomach and the brain. Okay, so step two is we're going to have a special side chain, pKa, of 7.0. And to visualize this, let me draw the actual structure of our histidine. See if we got room over here. So histidine structure. So it's going to be our mount-top backbone, line off to the right, our OH, our double-lined oxygen. That's going to give us our carboxylic acid. And we're going to have a H2N amino group here, line that comes off the top here, line off to the right, and we're going to draw a pentagon shape. A pentagon has 5 sides, so 1, 2, 3, 4, 5, double bond here, nitrogen, nitrogen, and our hydrogen. Now this is going to be our special side chain. That's our pKa of 7.0, which is the same thing as our imidazyl ring. So we have our imidazyl ring, and it's at a pK of 7.0. And remember, this is all occurring within the cell's stomach or the cells of the brain. Let's just say it's the stomach. So let's draw in our pKa here in this little human body figure we have of 7.0. So what do these numbers mean now, right? So let's look back at our Henderson-Hasselbach equation that we're talking about, and let's plug in some of these numbers. So we know we have a pH of 7.4 over here. Now, is 7.4 less than our pKa of 7.0? No, so we can cross that out. Now we have a pH of 7.4. Now, is 7.4 greater than our 7.0? Yeah, of course it is. But this is only 0.4 greater, so it's really not this, it's more this right here. Our pH is roughly equal to our pKa. So step 3 is that we're going to have a histidine, which is going to be 50% protonated and deprotonated. And why this is important is because it being 50% protonated and deprotonated means it's a very useful amino acid within our active site of our protein, because it can stabilize or destabilize our substrate. So this is why histidine has a special side chain or is a special case amino acid, because it's imidiesyl ring, which makes it amphoteric, and we explain why it's amphoteric through our Henderson-Hasselbach equation. And that's histidine for you guys. And now I'm going to discuss proline and glycine. And I think really I can talk about these ones at the same time, because they are both going to be, the reason that makes them special or have special side chains is because they're both going to be something called alpha helix breakers. And what our alpha helix is, so to understand what an alpha helix is, it's going to be an amino acids winded up. So basically just coiled polypeptide chains. And to kind of understand why they're alpha helix breakers and what the heck is going on, is we need to understand the structure. And that's why I went over the amino acid structure in the very beginning, because that's pretty much our backbone for everything. So let's start here with proline. So proline, let's do this step by step. So step 1, to draw out proline, our side chain is going to wrap to form a secondary alpha amino group. Now, what the heck is a secondary alpha amino group? You're probably wondering. So what that is, it's going to be when our side chain forms a second covalent bond with our alpha nitrogen. Okay, cool. So we got the steps right here. So now we can draw it out. So let's see if I can fit it in right over here. So our proline is going to be a mountaintop backbone, line off to the right. We have our OH, double line oxygen there for our carboxylic acid. Now remember, we're going to wrap to form a secondary amino group. So we're going to be wrapping to the left, and we're going to be wrapping in a diamond pentagon shape. So pentagon has 5 sides, 1, 2, 3, 4, 5. Here's going to be an NH there, and that is going to be our alpha nitrogen. And also what is going to be there is our second covalent bond, and this whole area is going to be our secondary alpha amino group. And this whole thing right there is our side chain. So this secondary alpha amino group is going to mean something. I'm going to explain what that means to you here in a bit, because it's very important, this secondary alpha amino group that's formed. It's going to do something very special to our polypeptide chains. So let's go through the structure of proline first. So let's see if I have some room for proline. So step one to draw the structure of proline out is going to be our side chain is going to be a single hydrogen. So when we have a single hydrogen, that's going to mean something for us. That means we're going to have a alpha carbon that is not going to be a chiral carbon. Now, you're probably wondering, what the heck is a chiral carbon? Well, it's an asymmetric carbon. Maybe that didn't help very much. So let me break down asymmetric a little bit more for you. So what that means is we're going to have 4 different atoms or groups on our carbon. Okay, so glycine, guys, drawing out the structure. So like I said, we said step one, single hydrogen side carbon, and now we're going to go ahead and draw that out. So glycine, and we're going to draw that out in a 3D wedge and dash format, because I really want you to visualize where the hydrogen is at. Well, hydrogens actually. And the wedge and dash format of our amino acid structure is going to help explain that a little bit. So we're going to have our mountaintop backbone here. We're going to have our OH, double line oxygen carboxylic acid, as normal. Our H2, N, and let's go ahead and draw in our hydrogen. So this is going to be our hydrogen side chain. So there's our H, which is going to be our side chain. So it's just going to be a single hydrogen. And I drew it in as a wedge because the wedge is going to tell us that the hydrogen is coming towards us. So this is kind of like a 3D structure. So imagine this being planar, but the hydrogen just coming towards me. So this is going to be our alpha carbon here. So with this side chain, this amino acid structure is not really stable. It's missing something. We only have, 3 groups here, our carboxylic acid, our amino group, and then our side chain. That doesn't really complete it. This isn't like stable. So to stabilize it, another hydrogen that's separate from the side chain is going to be added. And this one is going to be going away from us. So away. So we have a hydrogen coming towards us and a hydrogen going away from us. And this kind of creates a little problem, because we talked about an asymmetric carbon, which is a chiral carbon, and there has to be 4 different atoms or groups on the alpha carbon. And we have an H duplicate here now. So what does that H duplicate mean? It means this alpha carbon is not chiral. So we have no chiral alpha carbon. And what's happening here, since our side chain is so small, it's just a single hydrogen atom, this is going to be a very flexible amino acid structure. It's going to be moving around a lot. It's just very flexible. So we have lots of flexibility. And this is going to mean something very important as well. I'm going to explain what that means. As well, I'm also going to explain what our secondary amino secondary alpha amino group means for our proline. So I told you guys that I would explain what our secondary alpha amino group of our proline and our what do we have here? No chiral alpha carbon and the flexibility of our glycine means. These two things are going to do something very special. It's going to disrupt a certain pattern of ours, a very important pattern. So disrupt our pattern of our secondary protein structure. And what our secondary protein structure is, it's actually an alpha. Oh, there's our, shoot, where's our alpha helix. And what an alpha helix is, just remember I told you, it's amino acids winded or basically just coiled polypeptide chains. And what our alpha helix looks like, just like this. So our secondary alpha amino group is going to disrupt this pattern, and our no chiral alpha carbon and the flexibility of glycine is going to also disrupt this pattern. And how it's going to disrupt it, it's going to add kinks. Each of these are going to add kinks to our alpha helix. So instead of our alpha helix looking this nice little spiral shape that it normally looks like, it's going to look all distorted. It's going to look a little bit like that. That's what proline is going to do. And the same thing with glycine. It's going to make this beautiful alpha helix look like that. And these are two very important things, our secondary alpha amino group and our no chiral alpha carbon and the flexibility, because it disrupts this alpha helix. This is one of the most important things. And that's proline and glycine. So finally, guys, we're going to talk about my friend cysteine over here. So the reason why our cysteine has a special side chain is because something kind of cool, our thiol group. And our thiol group is simply just a SH. And what happens with our thiol group is our side chain forms a disulfide bridge. Now, what is a disulfide bridge? Sounds kind of cool, right? So a disulfide bridge is just going to be a strong bond between two sulfur atoms of two close cysteine amino acids. Okay, sounds pretty simple. So to understand how all this comes together, we're gonna have to talk about something called redox reactions. And what is that? That is reactions that gain or lose electrons. So the easiest way to think about this is using an acronym called oil rig. Yeah, that's right, oil rig. So the platform drillers sit on in the middle of the ocean where I guess they drill oil up. So an oil rig. So let's break down our acronym. So we have O, which is going to be oxidation. We have I, which is going to be is. L, so we have oil. loss of electrons. And now let's do rig. So R is reduction, I is G. Probably guess that it is gain of electrons. Okay, so there's our acronym. So really for redox reactions, all you really need to know is this acronym right here. And to understand how you use this, let's just do our example with cysteine here. So I'm going to give you a little example. And we're going to have 2 cysteines. And we're going to go step by step. So step 1 is we're going to start off in a reducing environment. So reducing environment. And that means we're going to be in an intracellular space. So intracellular space. So what's intracellular space? You're probably wondering. I mean, that is going to be within a cell. So intracellular within a cell. So these cysteine amino acids are going to be occurring within a cell. So let's visualize this, what we have going on here. So let's draw this out. See if I can fit this in right here. So we're going to have our regular amino acid mount top backbone, line off to the side, our regular OH, double line oxygen here. We're going to have our H2N amino group. That's our carboxylic acid group, of course. And we're going to have a CH2SH here. Okay, and now remember I told you it's between 2 sulfur atoms of 2 close cysteine amino acids. So our side chains are going to have to be pretty close together for any sort of like reaction to like occur. They can't just be floating around like kind of very far apart like in our cell. They have to be close together. So I'm going to draw our side chain. So this is our side chain. I'm going to draw the second cysteine side chain close to this. So we have a CH2SH. And we're going to draw our amino acid kind of upside down a little bit. So we're going to have an upside down amino acid mount top backbone. We're going to have a line off to the right. That's going to be our OH. We have our double line oxygen here. Our H2N here. Okay, great. So now we have our 2 cysteine amino acids. And our thiol groups, remember, it's just an SH. So here's our thiol groups. So these are the thiols in reduced form. So another thiol in reduced form. And nothing here is really happening. We have our amino acids close together, our cysteine amino acids, but nothing has really happened because we're in reduced form. And reduced form, if you look at our oil rig acronym, reduction is a gain of electrons. So if we have our hydrogen present, that means we're going to be gaining we have a gain of electrons. So hydrogen is present. We're going to have a gain of electrons. So we really have no reaction occurring. Where we have our real reaction going is going to be our step 2, when we're going to be in an oxidizing environment. And that's when we're going to be in an extra cellular space, meaning, let's see, outside our cell membrane. So just outside the cell. So our 2 cysteine amino acids, they're going to be outside the cell, floating around somewhere. So extracellular space. So let's see if we can get this drawn out now. So we're going to be in our oxidizing environment. So like I said, that's our extracellular space. So now I'm going to go ahead and draw out, visualize kind of what's happening with, our oxidizing environment when we have our 2 cysteines. We already saw what happens when we draw it out in an intracellular space. Let's find out what happens outside the cell now. So we're going to have our two cysteines here. So we're going to have our mount-top backbone, line off to the right, OH, double-lined oxygen here, our H2N amino group, and we're going to have our CH2, but just an S. Now remember, these amino acid side chains have to be near each other. So here's our second side chain, so CH2S. And this amino acid is going to be upside down, mount top amino acid backbone right there, line off to the side. It's going to be our OH, double line oxygen here, and our H2N amino group. And notice how we don't have that hydrogen anymore. What's going to happen is when we form a disulfide bond right here, because these two bonds between the sulfur groups are going to react and form a disulfide bond. So when you lose a hydrogen, so we're in oxidized, so we're in oxidized, so we're going to lose an electron, so we're losing a hydrogen, so no hydrogen equals loss of electrons. So no hydrogen equals a loss of electrons. So when we form this bond between our sulfur groups, we're actually going to lose our electron, and we're going to be in an oxidizing environment. And that's where our disulfide bridge is going to be formed. And our disulfide bridge is what really is going to make this whole cysteine amino acid special, because the thiol group, which is the SH, forms that disulfide bridge, and it being in the oxidizing environment in the extracellular space outside the cell membrane forms the whole cysteine reaction to get the disulfide bridge. So for cysteine, this is how our thiol group forms our disulfide bridge, and this is why cysteine has a special side chain which makes it a special amino acid case. So we talked about histidine, proline, glycine, and cysteine, and those are our 4 amino acids that have special cases or special side chains. And you guys learned about redox reaction, the Henderson-Hasselbach equation. You guys learned how to draw the structures of histidine, proline, glycine, cysteine. You learned what a disulfide bridge is. We learned a lot today. Thank you guys for watching. If you guys want to watch more, view here or subscribe there. Show me some likes if you love what you're watching, and bye guys.